We will work on another example regarding maximum stress data theory. Find the off-axis shear strength of a 60-degree graphite epoxy laminate. First of all, what is off-axis shear strength? This is asked in this problem. Off-axis shear strength. And this is related to pure shear loading. Is the smaller of the magnitudes of positive and negative shear stresses applied at the point of failure. Point of failure. And therefore, this is related to pure shear loading of excess shear strength. You can consider examine two different plies. Suppose that this is ply number 1. This is our ply number 1 with these fibers. And I'm applying a positive shear if that is the global axis. This is the positive shear direction. Pure shear loading. An angle lamina under pure shear loading. Suppose that the intensity of loading is tau 1, as or stress level is tau 1. Consider the same lamina, same one. But I'm going to change the direction of stress. Suppose that we are reorienting the stress. Still, these are global axis. And stress is applied in the other direction, a negative stress. Negative shear is applied. To the laminate. And that negative shear at the point of failure is tau 2. And you have different stress amplitudes in these loading cases. You can find tau 1 for failure and tau 2 for failure of excess shear strength of excess shear strength is the smaller magnitude is equal to smaller of the magnitudes applied here. For this is minimum of absolute value of tau1 and absolute value of tau2. We have to find tau1 and tau2, whichever is smaller is going to give you the off-axis shear strength. And you can do this by applying maximum stress failure theory. We'll be able to determine this. Now, generic case, let's start with generic case. I'll copy this one more time. Suppose that this is stress. And I'm going to denote this stress as tau. Tau can be positive or negative. And what are the local stresses under the application of tau? Because we need local stresses to apply maximum stress theory. Local stresses, sigma 1, sigma 2, tau 1, 2, T times sigma x, sigma y, tau xy. And what is sigma x here? What is sigma x in this problem? Any answers?
Isn't it 0 hocam?
Yes, sigma x is 0, that's right. Sigma y is also 0. Non-zero stress is tau. And by transformation, you'll be able to find local stresses. Sigma 1 is 0.866 tau. Sigma 2 minus 0.866 tau, and tau 1, 2 is minus 0.5 tau. These are no. When I will apply maximum stress failure theory, strength parameters, follow from table 2.1 again, the same parameters actually, because again we are considering graphite epoxy laminate, and write down the inequalities for maximum stress failure theory. Substitute the numerical values of the strength parameters, and you will get minus 1500 less than 0.866 tau, and that is less than 1500. This is the first inequality. The second one is minus 46 less than minus 0.866 tau, is less than 14. The third one related to tau 1, 2, minus 68 less than minus 0.5 tau, is less than 68. Each is in megapascals. I can now determine positive and negative values for tau. Divide 1 by 0.866, and you will end up with minus 1,732.1 less than tau. That's less than 1,732.1. That's from 1. From 2, divide by minus 0.866, and if you divide an inequality by a negative number, the direction is changed. Therefore, you'll find 204.06 greater than tau, and that's greater than minus 46.19. In a similar way, from 3, we find 136 greater than tau, and that's greater than minus 136. And it's possible to determine the limiting values. What is the positive shear stress at failure? Positive shear stress at failure, according to these results. Tau1. What's the positive shear stress at failure?
136, is it?
Yes, that's right. 136 megapascals. Now, this particular value is the smallest of these positive stresses that causes failure. So this is the limiting value. And second question, negative shear stress at failure. Negative shear stress at failure. That's going to be designated as tau2. And what's the negative shear stress at failure?
Minus 46.19.
Yes, that's right. This is the smallest magnitude for negative stresses, and that's going to lead to failure minus 46.19 megapascals. And the off-axis shear strength is based on the minimum of these off-axis shear strength is that equal to, what is it? What's the off-axis shear strength? The value with the smaller magnitude should be chosen, which means that pure shear strength is 46.19 megapascals. This is the off-axis shear strength or strength of the lamina under pure shear load. And it is resulting from this local stress sigma 2. That's also an important point. The stress. Any questions about this example? I've already defined strength ratio. And the first example was also related to the strength ratio. And for this reason, we can talk about the second failure theory. And this is named as Tsai-Wu failure theory. Tsai-Wu failure theory. Experimental analysis has to be carried out to see whether a failure theory or an hypothesis produces sufficiently accurate results. I will talk about comparisons between the theoretical results and the experimental results. Maximum stress theory was the first one. In the book, you'll be able to find maximum strain theory, Tsai-Wu theory, and as a more general theory, which accounts for the unequal strength values. That is Tsai-Wu failure theory. And this failure theory is based on the total strain energy, total strain energy, failure theory, of Marchari. And I'm going to give the inequality related to this failure theory. It's based on the energy approach. And apply is considered to be fair if this inequality, H1 sigma 1 plus H2 sigma 2 plus 6 tau 1 2 plus H11 sigma 1 squared plus H22 sigma 2 squared plus H6 6 tau 1 2 squared plus 2H12 sigma 1 sigma 2 less than 1. as is the general rule, and applies constant to be failed if this inequality is violated. Now there are a number of coefficients here. You see these coefficients, H1, H2, H6 to H12. And they are found by considering simple loading conditions for a unidirectional laminate. And the coefficients are found by considering basic loading conditions on a unidirectional laminate. And what are these basic loading conditions? We were dealing with a unidirectional laminate to find these coefficients. Suppose that this is the unidirectional laminate. And these are 1 and 2 axes. Apply simple loads. For example, uniaxial loading in one direction. This is uniaxial loading in one direction. Suppose that the magnitude or intensity is sigma 1 T ultimate. Sigma 1 T ultimate is applied to a unidirectional lamina, and what will happen in that case? What is your prediction? What happens if you apply such a loading? Unidirectional lamina we are applying the limiting stress, fails under this load. And loading is sigma 1 equals sigma 1 T ultimate, and sigma 2 equals tau 1 2, and these are 0. Failure occurs, and failure conditions should be satisfied in this equality. And at the point of failure, there's an equality. The case of equality is valid. This is substitute into the Tsai-Wu condition. This Tsai-Wu condition. We have H1 sigma 1 T ultimate H1 sigma 1 T ultimate. And second one is 0. This is 0. H1 1 sigma 1 T ultimate squared plus H1 1 sigma 1 T ultimate squared. And what else we have? 0, 0, and these are all 0. And at the point of failure, this left side should be equal to 1. This is one of the basic loading conditions and considered compressive loading. Consider compressive failure loading. What is sigma 1 in this loading? Compressive failure loading. What is it equal to?
Sigma 1 T ultimate.
Yes, again, but this is compressive. We need to substitute minus sigma 1 C ultimate. Sigma 2 equals tau 1, 2. And these are 0. Substitute this into Tsai-Wu condition, and you'll find minus H1 sigma 1 C ultimate plus H11 sigma 1 C ultimate squared is 1. Again, I'm going to name or number these as 1 and 2. And solving 1 and 2 for H1 and H11, you'll find H1 equals 1 over sigma 1 T ultimate minus 1 over sigma 1 C ultimate. This is the first coefficient.